So welcome to another exciting video about rocks and fossils. My name is Benjamin Berger. I'm an associate professor of geology at Utah State University. And in this two-part video series, I'm going to summarize the 10 most common methods of finding the age of rocks and fossils. So this is the second part where we talk about the next 5 most common methods of discovering the age of rocks and fossils. So in the first video, I listed the following methods: radiocarbon dating, potassium-argon dating, argon-argon dating, fission track dating, and uranium-lead dating in zircons. One of the things that you will note about these methods is that they are used either to date organic matter that's less than 100,000 years old, or volcanic or igneous minerals that are much older, between 1 million to 5 billion years old. So that leaves us with a lot of materials that we can't date using those methods, including fossils directly that are over 100,000 years old, and sedimentary rocks, since detrital zircons will only give you the date when they turned to a solid crystal, rather than the age of the sedimentary rocks that they're found in. So using these methods, we can't determine the age of a stone or a clay pottery artifact, the age of glacial features on the landscape, or fossilized bones directly. Now, one of the places that it's notoriously difficult to date are cave deposits, particularly cave deposits that contain early species of humans, which are often older than the limits of radiocarbon dating. So this problem is exemplified by the controversial ages surrounding the Homo florensis discovery, which is a remarkable teeny small species of early humans known as the hobbit, that were discovered in 2003 in a cave located on the island of Flores in Indonesia. Physical anthropologists have argued that the species shares morphological similarities with Homo erectus, which lived in Indonesia from 1.49 million years ago to about 500,000 years ago. Homo erectus was the first early human to migrate out of Africa, and fossils discovered in Indonesia are some of the oldest, as determined by potassium-argon and zircon fission track dating. However, radiocarbon dating from the cave where the tiny species Homo florensis was found are much younger than expected, yielding radiocarbon dates of 18,700 years to 17,400 years ago, which indicates a very late Pleistocene age for the fossils, which is old, but not as old as paleoanthropologists had suggested if the species was closely related to Homo erectus. So kind of stunned by these more recent radiocarbon ages for the skeletons, researchers decided to conduct a second analysis, and they turned to something called luminescence dating. There are 2 types of luminescence dating: optically stimulated and thermally stimulated. They basically measure the time since the sediment or the material was last exposed to sunlight, optical, or heat, thermal. Now, luminescence dating was developed in the 1950s and 1960s, initially as a method to date when a piece of pottery was made. The idea was that during the firing of clay in a pottery kiln, which hardens the pot, the quartz crystals within the pottery would be subjected to intense heat and energy, and the residuals of that would dim slowly long after the pottery was cooled down as a sort of residual energy. Now, early experience in the 1940s on heating crystals and observing the light emitted after subjecting the crystals to heat or light, and these experiments showed that materials would either fluoresce, which would mean that they would spontaneously glow, or phosphoresce, where there was a delay in the light given off of the material for a longer period of time, long after the material was subjected to the initial light or heat. So if you've ever played with glow-in-the-dark objects, you can see this when you expose an object to light and then you turn off the light, and there's this glow to the object for a long time, for a long while, until it dims to the point where you can't see it anymore. So that effect is called phosphorescence. It was also known that material near radioactive materials would also give off either spontaneous fluorescence or phosphorescence, which would last. So it doesn't have to be heat or light. Radioactive particles can also excite material to glow as well. Now, it was theorized that exciting the electrons in the atom with intense heat or exposed to sunlight, photons, or to radioactivity, the electrons would become excited and they would move up energy levels. However, these electrons would quickly drop down in energy levels, emitting photons as observable light when the object was cooled or was removed from the light. In some materials, these electrons would become trapped at these higher energy levels and slowly pop back down to lower energy levels over a much more extended period of time. When electrons drop down from their excited states, they would then emit photons. And this prolongs the glow of the material over a longer period of time, and perhaps thousands of years. So scientists wanted to measure whether in ancient clay pots there was some remaining trapped electrons, which would show a dim glow. The dimmer the glow observed, the older the pottery would be. So early experiments were successful, and later this tool was expanded to materials exposed to sunlight rather than heat. Now, the way it works is to determine two things. First is the radiation dose rate, as this will tell you how much radiation the crystal has absorbed over time. This is usually done by measuring the amount of radioactive elements in the sample and surrounding it. The second thing to measure is the total amount of absorbed radiation, which is measured by exposing the material to light or to heat and measuring the number of photons emitted by the material. So using these two measurements, you can calculate the age since the material was subjected to initial heat or light. The first is TL, or thermal luminescence dating, using heat to measure the amount of photons given off of the material. And the second is infrared stimulated, or IRSL. And the third is optically stimulated, or OSL, which refers to how the photons are measured in the lab by stimulating them with either infrared light or visible optic light. Now, the technique works well, but there is a limit to how dim the material can be to give you useful information. So it works well with materials that are 100 to about 350,000 years old. So similar ranges to radiocarbon dating, but it can be carried out on different materials such as pottery, stone artifacts, and the surfaces of buried buildings and stonework. Now, it's not used very much in paleontology, but here at Utah State University we have an OSL lab that's run by Dr. Tammy Rickner, who teaches classes about how to do this type of dating. So it's very useful in archaeology, geomorphology, and in dating soils. Now, researchers, in addition to determining the radiocarbon age of Homo florensis, used thermoluminescence dating and found a TL maximum date of 38,000 years old and an IRSL minimum date of 14,000 years old, suggesting the 18,000-year-old date was correct for the skeletons found in the cave. And it's interesting because this younger date resulted in a number of scientists arguing that the fossils were abnormally small modern humans. However, further dating was carried out. One of the arguments questioned how closely associated the samples were that were dated were located to the actual fossilized skeletons found. So in 2016, a new team reported on new OSL dates bracketing the skeletons, and they found dates between 65 and 71,000 years old sediments above the skeleton, and 89 to 128,000 years below the skeletons, so making the estimated age of these fossils much older than the previous team. Now, the trouble with these dates is that they're telling you the age that these sediments were last exposed to sunlight, and not when they were deposited in their current place. So there's probably a lot of mixing going on inside the cave. Furthermore, the radiocarbon dating is kind of close to that maximum reliable level, and hence might be underestimating the age. So was there another method that we could use and measure the actual bone of these fossils, of these fossil skeletons? And that's where uranium series dating comes in. Now, we talked about uranium as this large atom which decays to a very long half-life to lead, and that there are two uranium decay chains, one for uranium-235 and one for uranium-238, both going down to different isotopes of lead. Now, one thing that we can look at is just a segment of that long decay chain, the decay of uranium-238 to uranium-234, which is the first part of this process of uranium-238 decay. In particular, we can look at the uranium-234 to thorium-230 decay. Now, uranium-238 decays to thorium-234 with a half-life of 4.27 billion years, and thorium-234 decays to protactum with a half-life of 27 days, and then protactum-234 decays to uranium-234, also with a half-life of 27 days. And finally, uranium-234 with a half-life of 245,500 years decays to thorium-230. And the decay between uranium-234 and thorium-230 can be used to measure things within a few 100,000 years. Now, there is a problem with this method, and that is that we don't know the initial amount of uranium within the bone or sediment that we are measuring, as there is an unknown amount of uranium-234 in the bone or sediment as a result of uranium oxide being carried by groundwaters moving into the fossils and pores between the sediment grains. So unlike other dating methods where the initial amount of daughter product was assumed to be zero, or we had a way to determine it experimentally, such as in carbon-14 dating, we can't make that case. So what we have to do is we have to build a diffusion model. Often this is called modeling ages. The way this is done is that the bone is sectioned, it's then cleaned, and then laser ablated at various points across its depth, measuring the ratios between uranium-234 and thorium-230. Because the bone absorbed more uranium-234 over time, the outer layers of the bone will be enriched in uranium-234 compared to the internal parts of the bone. So then we're using a gradient of uranium-238 and uranium-234 and thorium-230, and a diffusion model can be made to determine the amount of uranium-234 likely in the bone when the fossil organism died, and the amount of thorium-230 resulting from the decay of this original uranium-234, as additional uranium-234 was added during the fossilization process. Now, because of this addition of uranium-234 and the fact that uranium-234 is very rare, it's only produced by the decay of uranium-238, this method is kind of reserved for very difficult cases, such as dating fossil deposits in hard-to-date cave deposits, especially in the upper limits of radiocarbon dating between 100 and 500,000 years old fossils. So uranium series dating was used to re-examine the Homo florensis by looking at the actual fossilized bone itself to hope to resolve this question. Now, the uranium series dating of the bone of Homo florensis resulted actually in ages between 87 and 66,000 years old. So it's older than the radiocarbon dates from nearby charcoal, and giving it an age based on the actual fossilized bones themselves. Now, this was also done with more modern human fossil bones that were stratigraphically above Homo florensis fossil that were found in the same cave, and they had radiometric dates of 9.5 to 6.4 thousand years ago, and they revealed uranium series dating of 7.5 thousand years ago as sort of an independent test. So uranium series dating is becoming more widely used because it can directly measure the fossil itself. However, these are modeled ages, since you have to determine the diffusion of uranium into the pores of the bone as it was fossilized in the cave, and it's fairly destructive to the fossil too. Now, uranium series dating was also done for another problematic early human cave discovery, the age of Homo natali from the Rising Star Cave in South Africa. Fossil teeth were directly dated using uranium series dating in that case, and they yielded a minimum age of 200,000 years old, which they had been predicted to be about 1 million years old. So I was kind of surprised when the uranium series dates came back. Uranium series dating from the rocks surrounding the fossils indicate ages that bracket between about 500,000 to 242,000 years ago. And using other methods have suggested the fossil may be around 253,000 years old. So uranium series dating tends to have large error bars due to the modeling of the diffusion of uranium into the fossils and rocks. And this all, of course, is depending on how quickly and how much uranium-238 and uranium-234 was added to the fossil over time in the cave. Uranium series dating is used really only in special cases where traditional dating such as radiocarbon dating and uranium-lead dating can't be done. Electron spin resonance, ESR. So in April of 1986, the Chernobyl nuclear power plant suffered a critical meltdown, resulting in the explosion and fire that released large amounts of radioactive materials into the nearby environment. The accident led to the death of 31 people directly from radiation, and 237 suffered acute radiation sickness. Worry spread across Europe as to how to measure the exposure to radiation from the accident. The electron spin resonance was developed by Soviet scientists to measure the exposure to radiation by looking at teeth, particularly the lost baby teeth of children living in the area. Electron spin resonance is the measurement of the number of unpaired electrons within atoms. So when exposed to radiation, electrons will unpair from covalent bonds and become unpaired within the orbitals, resulting in a slight difference in the magnetism of the atom. This radiation damage results in the breakage of molecular bonds, and the reason radiation causes cancers and damages cells, since at the atomic level, large organic molecules break, resulting in abnormally high errors in DNA, RNA, and proteins within the cells. So electron spin resonance measures the amount of free radical electrons within a material. So using this measurement, scientists measured the amount of electron spin resonance in teeth from children who lived near the accident to determine the amount of exposure they had to radiation fallout from the Chernobyl accident. The study worked, which led to the idea of using the same technology in fossilized teeth exposed to naturally occurring radiation in the ground. Now, dating using electron spin resonance requires that we know the amount of uranium and radioactivity that is in the surrounding material through its history and calculate the length of exposure time to this radiation. The issue is that you have to model the amount of uranium uptake within the fossil over time, similar to the model that you develop with uranium series dating. This is because in both methods of dating, you can't assume that uranium and the amount of radioactivity in the material remain the same, as the uptake of fresh uranium over time likely occurred. Often scientists will focus on the dense crystal lattice structure of enamel in teeth, a mineral called hydroxide apatite, as it is less susceptible to the uptake of uranium. So electron spin resonance is often paired with uranium series dating, since it has a similar range of ages that it can be used for from a few hundred to up to 2 million years. So unpaired electrons within atoms is a more permanent state than electrons at higher energy levels seen in luminescence dating. So older fossils can be dated up to about 2 million years. Now, of course, this dating method can't be used for the vast majority of fossils that are older than 2 million years old, but it can be used to date the length of time a fossil or rock has been buried up to that limit. So note that electron spin resonance dating is determining the length of time a fossil was buried in sediment that has background radiation that can be measured. So the next method we're going to actually look at is the length of time something was, well, the opposite, the length of time it was exposed to sunlight. Surface exposure dating, or beryllium-10 dating. So this is a method that has kind of really revolutionized the study of past ice ages during the Pleistocene epoch over the last 2.5 million years ago, and the study of glacial and interglacial cycles of Earth's recent climate. Surface exposure dating determines the length of time a rock has been exposed to the sun. Now, ascertaining the length of time that the rock has been exposed to the sun allows geologists to discover the age when that rock or that boulder was deposited by a melting glacier, and the time of the timing of the extent of those glaciers at the local level throughout past ice age events. So the way it works is that when rocks are exposed to sunlight, they're bombarded by cosmogenic rays from the sun, which contain neutrons. Now, these rays result in something called spallation of the atoms in mineral crystals, resulting in the buildup of cosmogenic nuclides. Now, there's a number of different types of cosmogenic nuclides. For example, we had previously talked about potassium-40 being hit with neutrons in a lab setting and producing argon-39. So the same thing happens in nature when rocks are left in the sun for a long time. You can actually measure the amount of argon-39. Most geologists instead look for atoms which form solids, as they're kind of a little easier to extract from the rock, including beryllium-10, aluminum-26, carbon-14, you can actually use that, and chloride-36. And isotopes of various noble gases like argon can be used. One of the most widely used cosmogenic nuclides to measure is beryllium-10. Now, beryllium-10 is not found in quartz minerals when they form, but will accumulate in quartz when the oxygen atoms within the crystal lattice structure are exposed to cosmic rays. The beryllium-10 will build up within the crystals as long as the rock is exposed to the sun. Now, beryllium-10 is unstable. It's radioactive. It's a radioactive isotope with a half-life of 1.39 million years, kind of making it ideal for applications of dating during the Pleistocene epoch. Most rocks studied so far have exposure ages of less than 500,000 years, indicating that most rocks get reburied within 500,000 years. Now, surface exposure dating is different because what we're looking at is at the amount of beryllium-10 building up within the surface of the rock over time. So the more beryllium-10 is within the rock, the longer it has been exposed to sunlight. Now, if the rock becomes obscured from the sun through burial or a tree growing next to it, then the buildup of the beryllium-10 will be slowed or turned off, and over time will decay to boron, emptying the beryllium-10 out of the rock and resetting the clock for the next time it is exposed to the sunlight. Geologists have to be sure that the rock is well exposed to sunlight and not shaded by any natural feature in the recent past, like trees. Geologists will select a boulder or rock and carefully record its location, as well as the horizon line surrounding the rock, to account for the length of sunlight exposure of any given day at that location. A small explosive charge is drilled into the rock, and rock fragments are collected from the surface edge of the rock. The sample is ground into a powder back in the lab and digested with hydrofluoric acid to isolate quartz crystals, which is turned into a liquid solution with a very strong acid. This solution is reacted to various chemicals to isolate the beryllium into a white powder, which is then passed through a mass spectrometer to measure the amount of beryllium-10 in the rock. The amount is then compared to a model of how much sunlight the rock was exposed to at that location with the topography of the surrounding features, and determine the length of time that the rock has sat there on the surface of the Earth. It's a pretty cool method that has become highly important in understanding the glacial history of Earth through time. All right, so we've made it finally to number 10. And there are a number of other methods out there that I almost thought of including on this list. One method I didn't include was uranium-thorium-helium thermochronology, which is the study of the buildup of radiogenic helium within crystals resulting from the decay chain of uranium. Now, uranium-thorium-helium thermochronology, as the name suggests, is the study of the thermal history of rocks as they move through the lithosphere at different depths and are subjected to different temperatures. It's not used in paleontology yet, but it could have applications in the dating of iron oxide minerals, which are found in fossils. The method was used in very early attempts to date rocks, but the helium would escape too easily from the rock, and often those dates would yield too young of ages. However, there's new technology, and there's been sort of a revision of the methods, and it's become a more important method, especially in studying metamorphic rocks and the thermal history of rocks in the subsurface. So we have a faculty member, Dr. Alexis Alt, who is researching new applications of this type of dating, and has some students working on developing new tools for dating different types of crystals other than zircons, which is kind of exciting and could have applications in paleontology in the future. Another method that did not make this list is rubidium-strontium dating, which has applications in paleontology. It's more frequently used in determining the age of meteorites, as the half-life is very long, 49.23 billion years. So it works really well with rocks that are billions of years old, but limited to igneous rocks, much like potassium, argon, and uranium-lead dating. So I decided to talk about, as the 10th one, magnetostratigraphy. And that's because it is extremely useful in paleontological studies and dating sedimentary rocks. Now, in a short video, I can't go into all the details of this method, and in fact, it deserves its own course, but I'll give you kind of a quick, brief outline. So magnetostratigraphy is the study of magnetic orientations of iron minerals within sedimentary rocks. These orientations record the direction of the magnetic pole when the sedimentary rock was deposited. The orientation of the pole switches every few 100,000 years, and this change in the orientation of iron minerals is recorded in the rock layers. Thus, measuring these orientations between normal polarity, when the iron minerals point northward, and the reverse polarity, when the iron minerals point southward, give you events in the past that can be correlated between different rock layers. The thickness of these bands of changing polarity can be compared to igneous volcanic rock as well, which record, of course, both the absolute age using like potassium argon dating, for example, as well as the polarity of the rocks at that time, allowing correlation between sedimentary and igneous rocks. Now, magnetostratigraphy is really important because it allows for the dating of sedimentary rocks that contain fossils even when there is no volcanic ash layers present. Now, there's a couple problems with magnetostratigraphy. One is that the rocks can become demagnetized in sedimentary rocks. So if the rocks are struck by lightning, it will scramble the orientations of the iron grains. It can also be difficult to correlate layers of rock if the sedimentation rates vary greatly or you have unconformities that you're unaware of. However, it works really well for many rock layers, and it's a great tool to determine the age of rocks by documenting these reversals in the rock record. So rocks are collected in the field by recording the exact orientation they are to the bedding plane. This is often done by writing on the rock the strike and the dip in situ, and then carefully extracting the rock as not to break it. The rock is then taken to a lab where the rock is placed in an iron cage to remove the interference of magnetic fields from the surrounding environment. And then the rock is cryogenically cooled down to extremely cold temperatures, just above absolute zero, where the residual magnetism of the rock will be easier to measure. And that's because sedimentary rocks are not very magnetic. So then the rock is slowly demagnetized and the orientation vectors are recorded and spatially plotted. Now these data points will fall either more toward the north or south, depending on the polarity of the Earth at the time of deposition. The time span between polar reversal events is really, really short, a few hundred years, with the majority of time the polarity in either a normal or reverse state. Sometimes the polarity changes very rapidly, while other times the polarity does not change for millions of years. Such a long interval of lack of change occurred during the Cretaceous, a period of 40 million years called the Cretaceous superchron, in which the polarity stayed normal for a very, very long time. So the magnetostratigraphy doesn't work well between 121 to 83 million years ago, but it has been used extensively for dating fossil-bearing units throughout the rest of the Mesozoic, as well as the Cenozoic and Paleozoic eras. All right, so those are the 10 most common or popular ways to date rocks. There are, of course, others out there, but these are the ones that I frequently encounter in my own studies of paleontology. I want to thank my Patreon supporters this week: Brian Clever, Pablo Luzato Figuez, Arcodis 1811, Justin Bovey, and Fred Olney. Thank you guys. If you want to learn more about supporting this channel and in the process get access to some behind the scenes videos, I'm going to be putting up some more Patreon only videos up on my Patreon page. Or if you just want to support my channel on YouTube, check out the link below in the description. And thanks for watching.